All right, so every region of neuron number 2 is positive 30, positive 30, positive 30, positive 30, right? All these regions are positive 30, okay, throughout the axon terminals and axon terminal buttons. All right, so if all these regions are positive 30, how is neuron number 2 ever going to be able to generate another action potential? The answer is it's not going to be able to as long as those regions are positive 30. And I've already told you a given neuron, some of them can generate over 1,000 action potentials per second. Okay, so that tells us something. As soon as these regions hit positive 30, we need to get them back to negative 70 so that another action potential can occur. Because think about it. If the hillock region is at positive 30, what triggers the hillock region, to generate an action potential? What's going to cause an action potential to occur within the hillock region? It's when it goes from negative 70 to negative 55. Well, if it's at positive 30, another action potential can't happen. So we need to do something called repolarization. We need to get all of these regions back to negative 70. So we're going to talk about how neurons repolarize. They do this incredibly quickly, beyond anything that our brains, ironically, because our brains are filled with neurons, but ironically, anything that we can really comprehend because it happens so quickly. Now, when I talk about this in 6116, it's very, very watered down. And I'm going to give you all of the detail as to how repolarizations and refractory periods actually happen here. So let's imagine this. The action potential is propagating down the axon of neuron number 2 here. Okay, and that's why I actually like to number these and not call them postsynaptic neurons, because the postsynaptic neuron is now going to become the presynaptic neuron, because I'm going to show you it hooking up with another neuron. The terminology is technically accurate. In looking at this, neuron number 2 is the postsynaptic neuron, but when you start talking about the neuron that the neuron number 2, the postsynaptic neuron, hooks up with, which we'll say is over here, now the postsynaptic neuron becomes the presynaptic neuron, so I just prefer to number them. So this is neuron number 1, this is neuron number 2, and over here we have neuron number 3. What I'm showing you is its cell body, its dendrites, and here we'll say is its axon. Okay. So neuron number 1 generated an action potential. It actually generated around 100 action potentials per second. And neuron number 1 then released a lot of neurotransmitters onto neuron number 2 over the course of a second. That allowed enough sodium ions to come in to neuron number 2 so that enough sodium ions actually got into the hillock of neuron number 2 to make the hillock rise to threshold. 15 millivolts more positive. Then the voltage-gated sodium channels in the hillock of neuron number 2 opened up. Sodium rushed in, made the hillock positive 30 millivolts. And what this really means is now we've generated an action potential. What's going to happen is, since we got neuron number 2 to get the hillock region within neuron number 2 to rise by 15 millivolts, negative 70 to negative 55, neuron number 2 is going to generate an action potential, a non-decremental electrical wave that's going to travel down its axon into its axon terminals and into its axon terminal buttons. The reason it's non-decremental, again, the voltage doesn't change as it propagates. That's because voltage-gated sodium channels line the length of neuron number 2. Neuron number 2's axon, I mean. Okay, so the action potential then propagates into neuron number 2's axon terminal buttons. And instead of voltage-gated sodium channels existing in the buttons, there are voltage-gated calcium channels, and they open up, which allows calcium to flow into the buttons of neuron number 2. That's the whole purpose of the action potential. The purpose of the action potential is to propagate into the buttons of that specific neuron and cause or allow for calcium to actually flow into the buttons of that neuron, so that then the influx of calcium can tell the vesicles within the buttons of that neuron to go to the distal end of the button and dock and release their neurotransmitters through exocytosis. So you can say, the purpose of the action potential is to cause exocytosis of neurotransmitters, which is true, but how is it actually doing that, right? Really, the purpose of the action potential is to flow into the buttons and open up voltage-gated calcium channels in the buttons so that calcium can come in, and then actually the influx of calcium is what triggers exocytosis of the neurotransmitter. So it's a little bit more nuanced than just simply saying action potentials cause exocytosis. It's more detailed than that. All right, so these neurotransmitters through exocytosis are now leaving the axon terminal buttons of the neuron number 2 that just had an action potential travel down. Now, what type of neurotransmitters are these? That's highly specific to the different regions of the nervous system, and even in that specific region of the nervous system, which type of neuron you're talking about. So all I'm going to say is that neuron number 2 is releasing some type of excitatory neurotransmitter. Maybe it's glutamate, maybe it's acetylcholine. It all depends on the neuron and the part of the nervous system that you're within. So it's impossible to talk about this, really generically and then, give you a specific neurotransmitter. I'm just going to say it's an excitatory neurotransmitter. What's this excitatory neurotransmitter going to do? Well, I just told you, let me erase this real quick. The neuron number 2 hooks up with neuron number 3. Okay. Here is neuron number 3's dendrites. Okay. So neuron number 2 synapses with the dendrites of neuron number 3. Neuron number 2's axon terminal buttons synapse with the dendrites of neuron number 3. And neuron number 2 is releasing excitatory neurotransmitters into the synaptic cleft. So you can imagine on the dendrites of neuron number 3, attached to the dendrites or embedded in the plasma membrane of the dendrites of neuron number 3, there are going to be ligand-gated channels that bind this specific neurotransmitter. And that neurotransmitter is going to bind to those ligand-gated channels on the dendrites of neuron number 3, and it's going to cause them to open up. And if it's an excitatory neurotransmitter, I can tell you the ligand-gated channels, again, are probably going to be these non-specific cation channels, which is going to allow for the influx of sodium ions into the dendrites of neuron number 3. Within the dendrites, we're going to get a small depolarization. Now, if neuron number 2 only generates one action potential, what I can tell you is, and you should know this at this point, that's not going to be nearly enough sodium to actually flow all the way into the region of the hillock of neuron number 3 and make the hillock get to threshold. Potentials that come from the dendritic regions are decremental, right? They dissipate as they move away from the site of origin because voltage-gated sodium channels don't exist until you get to the hillock. So if neuron number 2 only fires one time, you can be quite certain neuron number 3 is not getting to threshold. But if neuron number 2 can fire, let's say, 100 times over the course of a second, it will release enough excitatory neurotransmitters to bind to enough ligand-gated channels on the dendrites of neuron number 3 to allow enough sodium in, so that enough sodium will actually get in to the hillock region of neuron number 3 to make the hillock region 15 millivolts more positive, and threshold will be hit, and an action potential will then occur. And now, a non-decremental wave of electricity positivity, called an action potential, is going to propagate down the length of the axon of neuron number 3 and into the axon terminals and axon terminal buttons of neuron number 3. And now neuron number 3, will release through exocytosis its neurotransmitters, because voltage-gated calcium channels within neuron number 3's axon terminal buttons will open up and trigger exocytosis. And this is the way that neurons communicate with each other. Another way of saying this is the way that neurons pass action potentials to each other. And that is the end of this review portion of kind of neuronal communication. synaptic transmission and action potentials. What we will talk about from this point on is all going to be new material, because what we need to talk about next is how the neuron repolarizes and these things called refractory periods. They're incredibly important to understand different theories related to all different cells within the body, all sorts of different cells. At the beginning, I said I was going to combine all of it together, but I'm just going to use this video and the previous video as both review videos, and starting with the next video, lecture will be all new content. First things first, here we'll say, is the hillock region. Okay, you have to pretend that we just got the hillock region to threshold. Enough sodium ions coming from the dendritic regions of the neuron got into the hillock to get us to threshold of -55 millivolts. Then all the voltage-gated sodium channels opened up. Sodium rushed in and got the region to +30. Now the question has to be, how did we get to +30 and not, any more positive? Why does it just stop at +30? And what we have to do is we actually have to look much more closely at the voltage-gated sodium channels to understand what's going on here. This is a voltage-gated sodium channel. It actually has two gates on it. Okay. It has what's called an activation gate, which is here. It's depicted differently in different images because nobody truly has a perfect idea of what these look like. But there's an activation gate, and then there's what's called an inactivation gate. Okay, so what you have to imagine inside of the hillock, we'll say we're at -70 millivolts. What's closed at -70 millivolts is what's known as the activation gate. Okay, the activation gate is what will open if we can get the hillock region to threshold. Okay, let's say that we go from -70 to -55 millivolts. That's threshold. What's going to happen is the voltage-gated sodium channels are going to open. When I say voltage-gated sodium channels are going to open, what I really mean is the activation gates on the voltage-gated sodium channels are going to open. That's what this actually means. Now, we'll make more sense of this as we go. But at threshold in the hillock region, the voltage-gated sodium channels open, and specifically what that means is that the activation gates open up. And you can look at this image over here and see what the activation gates opening looks like. Okay, so the activation gates open, and then the sodium ions within the interstitial fluid flow into the hillock region and make the hillock region hit +30 millivolts, right? So we get a big influx of sodium ions into the hillock because the activation gates on the voltage-gated sodium channels have opened. Now here's what happens at +30 millivolts. At +30 millivolts, what happens is the inactivation gates on the voltage-gated sodium channels close. Okay? This isn't going to make a lot of sense initially, but it'll make a lot of sense in 10-15 minutes or so. Okay? So the inactivation gates, this gate down here, is what shuts at +30 millivolts. Now, generically, what you can say, and this is what I do in a course like 6116, is I just say, well, the voltage-gated sodium channels shut at +30 millivolts. It's much more detailed than that. Okay, at +30 millivolts, the activation gate is not what closes. The activation gate actually stays open. At +30 millivolts, what happens is the inactivation gate on the voltage-gated sodium channels close. And if the inactivation gate closes, then sodium ions can no longer enter into the hillock. So at +30 millivolts, we've prevented any greater influx of sodium ions into the hillock. That's one of the reasons why the hillock region gets stuck at +30 millivolts, the most important reason, excuse me. So let me try to draw this for you. Okay, I'm not going to draw it like I did in the other image, but it's just to show you this happening, not in real time, but You can kind of maybe visualize it a little bit better if I draw it, okay? So if we get from -70 to -55 millivolts, right, the Hillock region hits threshold, then the activation gates on the voltage-gated sodium channels will open, and sodium will rush in and drive the interior of the Hillock up to +30 millivolts. All right, at +30 millivolts, I'm going to draw this in red. At +30 millivolts, the activation gates on the voltage-gated sodium channels do not close. What closes are the inactivation gates. Again, no one really knows what these inactivation gates physically look like, at least to any meaningful degree, but we're quite confident there are two gates. Okay? And at +30 millivolts, these inactivation gates close, and no more sodium can enter into the Hillock through these channels. So this is the predominant reason that the Hillock gets stuck at +30 millivolts and doesn't become more positive, right? Because sodium's equilibrium potential is actually +60 millivolts. So more sodium could come in, right? But since the inactivation gates close, no more sodium can in fact enter. Now, the sodium ions within the Hillock are going to propagate into the next region and cause more voltage-gated sodium channels to open up so that the action potential continues to propagate, right? But that's not what we're talking about here. What we're talking about is specifically within the Hillock region, and then you can extrapolate to all the other regions as well. We're talking about why the Hillock region and thus all the other regions get stuck at +30 millivolts. So we can go over to this next region and just talk about it real quickly. As the sodium ions move from the Hillock region into the subsequently negative region and make that region more positive, the activation gates on the voltage-gated sodium channels within this region will open up. Sodium will rush in through the voltage-gated sodium channels, make this region +30, and at +30, the inactivation gates on the voltage-gated sodium channels in this region, right, those inactivation gates will close and no more sodium will come in, and that's why this region gets stuck at +30 millivolts again. Okay, so this is going to happen in every region of the axon and axon terminal. But we don't want to just get these regions to be stuck at +30. We want to get them back to -70 millivolts so that another action potential can occur. This is just another image of voltage-gated sodium channels showing you how the activation gate is depicted against the inactivation gate. I don't know, some people, myself included, it's helpful if I see things depicted in many different ways. And this is just another diagram depicting how voltage-gated sodium channels have activation gates and inactivation gates and how they're different from one another. Anyways, the situation that we're in right now is the interior of the Hillock is at +30 millivolts, and the inactivation gate on the voltage-gated sodium channels is closed. No more sodium can come in because the inactivation gates are shut. So what else is going to happen simultaneously at +30 millivolts? So you have to imagine this as the Hillock region. Okay, so we're at +30 millivolts. Two things actually happen at +30 millivolts. Okay, so over here we're going to say is a voltage-gated sodium channel. Okay, sodium rushed in through these voltage-gated sodium channels because their activation gates opened up when we hit threshold. Sodium rushed in, made the interior +30 millivolts, and at +30 millivolts, you can imagine the voltage-gated sodium channels activation gates stay open, but their inactivation gates shut. Okay, so the voltage-gated sodium channels inactivation gates close, and thus no more sodium can come in, and we're stuck at +30. The other thing that happens at +30 is voltage-gated potassium channels open. Okay, so embedded throughout the Hillock region, I'm going to depict this in another way too. Embedded throughout the Hillock region, there are voltage-gated potassium channels, and these voltage-gated potassium channels at +30 millivolts open. Okay, before I talk about what that means, think about the two things that happen at +30. At +30, the inactivation gates on the voltage-gated sodium channels close, and the voltage-gated potassium channels open. So if voltage-gated potassium channels open, we have to think about what this means. Potassium is high inside, it's low outside. It's a positively charged ion. It's high inside, low outside. So it has a chemical driving force to leave. And now the interior of the hillock is positive 30, which means the exterior must be about negative 30 approximately. That's not entirely accurate, but it's close. Okay, so the exterior is going to be approximately negative 30 millivolts. So in this case, potassium has not just a chemical driving force to leave, but it has an electrical driving force to leave because the exterior is negative 30. Okay, so potassium is being pulled out of the cell for two reasons, right? It has a chemical and an electrical driving force for it to leave right now when the interior of the hillock is at positive 30. So if a whole bunch of voltage-gated potassium channels open up at positive 30 millivolts, basically the hillock region becomes much more permeable to potassium at positive 30 millivolts, then potassium, it's a positively charged ion, is going to shoot out of the hillock. What's happening to the hillock right now? It's losing a whole bunch of positively charged ions because these voltage-gated potassium channels are opening. And that would mean that on the interior, the number of negatively charged ions is rising compared to the number of positively charged ions. So as the potassium ions are shooting out through these voltage-gated potassium channels, the interior is going to become more negative. It's going to begin to repolarize and move back towards negative 70 millivolts. Let's quickly look at that in another way and then get into some more intricacies of this. Okay, so here we have the hillock region. Okay. At threshold, what opened? We got to negative 55 millivolts. The activation gates on the voltage-gated sodium channels opened up. Sodium rushed in and made the interior rise to positive 30. Okay. At positive 30, what happened? The inactivation gates on the voltage-gated sodium channels closed. The activation gates are actually still open, but the inactivation gates shut, and that prevented any more sodium from being able to enter, so we get stuck at positive 30 millivolts. Simultaneously, I'll draw this kind of in bluish, voltage-gated potassium channels opened up at positive 30. Potassium, which is an ion, positive ion, that's high inside, low outside, now has both always a strong chemical driving force to leave, but it also now has an electrical driving force to leave because we've made the interior positive and now the exterior is negative. So if we open up these voltage-gated potassium channels, potassium is going to flood out through both a chemical and an electrical driving force. And now the interior of the hillock is losing these positively charged potassium ions, and it's going to begin to become more negative. We call this a repolarization. The hillock now is repolarizing back towards negative 70 millivolts. Now, in a more basic course, again, like 6116 or undergraduate courses that I teach, what I normally do is when I don't even talk about activation versus inactivation gates, I would just say, at positive 30, the voltage-gated sodium channels close and the potassium channels open. Potassium shoots back out until we get to negative 70. Then the potassium channels shut and the sodium channels have a capacity to open again. Okay, so we've repolarized back to negative 70. Another action potential can occur. Okay, again, it's much more complicated than that. So we're going to talk about it in much more detail here. Okay, so there's a variety of things that are going to begin to occur as the interior moves from positive 30 millivolts back towards negative 70. And this results in us needing to talk about what are called refractory periods. So we're going to start off by talking about why these activation gates versus inactivation gates are so important. Okay, so imagine this. Imagine that voltage-gated sodium channels only had activation gates. Just little mind game here. What would happen? We could still get to threshold. We'd reach negative 55 millivolts, and the activation gates would open. Sodium would shoot in. We would get to positive 30. And then, well, the activation gates would close again. Great. That makes sense, kind of, right? None of that should be a problem. The activation gates close at positive 30. Simultaneously, the voltage-gated potassium channels open. Potassium leaves through its chemical and its electrical driving force and drives the interior back towards negative 70. Now, here's the thing. What should happen as potassium is leaving and we move from positive 30 back to negative 55 millivolts? What should happen at negative 55 millivolts? The voltage-gated sodium channels should open again, right? Because their activation gates, if the voltage-gated sodium channels only had activation gates, and the activation gates shut at positive 30, and then you begin to repolarize back towards negative 55, back towards negative 70. But once you hit negative 55, the activation gate should open again, right? That's the problem that was easily recognized when discussing and theorizing about these sodium channels. When you repolarize back to negative 55 millivolts, the activation gates in theory should open again, and that should allow then for sodium to just shoot right back in, and well, now another action potential is happening, right? That would be hugely problematic. Why would that be problematic? Because the neuron would just keep generating action potential after action potential after action potential after action potential. There would be no rest whatsoever. There'd be no stopping the neuron from just generating one action potential after the next, after the next, after the next, after the next, after the next. We know that some neurons in our body can rest for long periods of time. Okay? So if neurons' voltage-gated sodium channels only had activation gates, then as soon as they begin to repolarize, the voltage-gated sodium channels their activation gates would open back up at negative 55 and another action potential would be generated. And this is why inactivation gates are so important. And here's why. Inactivation gates don't open at negative 55. Okay. So I won't go through the whole thing again. But when we are repolarizing, right, what's actually happening? When we got to positive 30, the inactivation gates on the voltage-gated sodium channels shut. And that prevents any more sodium from coming in. It's not the activation gates that shut. It's the inactivation gates that close, and that prevents any more sodium from being able to come in. Simultaneously, at positive 30, the voltage-gated potassium channels open, and potassium shoots out. That drives the interior from positive 30 back down towards negative 70, but we have to talk about what happens when we get to negative 55 millivolts. We get to negative 55 millivolts. Again, in theory, if there were only activation gates, the activation gates on the voltage-gated sodium channel should pop back open, and then sodium should shoot in. But here's the thing. What's closed are the inactivation gates. The inactivation gates are closed, and they don't open at negative 55 millivolts. So when you get back to negative 55, all of a sudden sodium doesn't start coming in again, right? Potassium just continues to exit, and you continue to move back towards the resting membrane potential. The inactivation gates are what actually allow for neurons and other cells to be able to repolarize beyond, past threshold of negative 55 or whatever threshold is for the cell. Because the inactivation gates don't open at threshold, they stay closed. So of course there has to come a point where the inactivation gates, kind of open back up and the activation gates close. And when is that exactly? This varies pretty significantly from one cell to the next, even one neuron to the next. But we know that it happens sometime between negative 55 millivolts and like negative 60 or negative 65. We'll just say sometime between negative 55 and negative 65, okay, in the case of this neuron here. Okay, so let's think about what's happening. Again, potassium is shooting out. Potassium is shooting out, driving the interior from positive 30 back towards negative 70, and sometime between negative 55 and like negative 65. Again, this varies from one cell to the next, and also the channels vary too, even in one specific neuron. Some will begin to reset around negative 55, some might begin to reset around negative 60. They're not all identical. Okay, that's become perfectly clear in the literature as well. But somewhere in this range here, the voltage-gated sodium channels reset. What that means is the voltage-gated sodium channels activation gates, let me say it a different way, the voltage-gated sodium channels inactivation gates pop back open, and the activation gates, do it in green, the activation gates close. We call this resetting of the voltage-gated sodium channels. They reset. Their inactivation gates open back up, and their activation gates close. They reset to what they reset to their original orientation that they were when we began this conversation. Okay? This is a huge component to understanding how neurons repolarize and ultimately the conversation of refractory periods. What this actually means now is somewhere between negative 55 and negative 65, right? The voltage-gated sodium channels reset. And now, if we can get the neuron back to threshold, these voltage-gated sodium channels will actually be able to open again. I'll talk about exactly what that means in a little bit here when we get to the refractory periods. But for now, I just want you to realize during repolarization, when we get back to negative 55, the reason the voltage-gated sodium channels don't just open again at negative 55 during repolarization is because of the fact that the inactivation gates on the voltage-gated sodium channels are shut and they don't open at negative 55. And then somewhere between negative 55 and negative 65, what you're going to see is the voltage-gated sodium channels are going to reset. The inactivation gates are going to pop back open, and the activation gates are going to close, and we're back to the orientation that we saw at the beginning. So once the voltage-gated sodium channels have reset, if we can get the interior of the hillock back to negative 55, then the voltage-gated sodium channels will actually reopen again, and we'll have another action potential. But this conversation is not over yet because the voltage-gated potassium channels are still open and we are still repolarizing. Repolarization is still occurring as the voltage-gated sodium channels are resetting because why? The voltage-gated potassium channels are still open. So let's try this out. Okay. We are at negative 65 during repolarization. What exactly does that mean? When we're back to negative 65, there's a couple things that are happening. The voltage-gated potassium channels are still open, so potassium is still flooding out. The cell has an increased permeability to potassium, so potassium is still shooting out, and the voltage-gated sodium channels are back to their original orientation. The inactivation gates are open, and the activation gates are closed. So here's what the average person would think, and this is what I talk about, like just a general, more simplified course. You would think once you get back to negative 70 millivolts, the voltage-gated potassium channels would shut, and they don't. you would think that the voltage-gated potassium channels would close and you would just be back to the resting membrane potential. And now if you get back to threshold, another action potential could happen, but that's actually not what happens. The voltage-gated potassium channels actually stay open. So at negative 70 millivolts, you would think that you're back to the resting membrane potential. Okay? But here's the thing, because these voltage-gated potassium channels stay open, you're not back to the resting membrane potential, because transiently there's an increased permeability that the cell has to potassium. Let me explain. Okay, you have to go back and you have to think about regular resting membrane potentials. With a regular resting membrane potential of negative 70 millivolts, it's partly, mostly due to the fact that the cell has about 100 more leak channels for potassium, than it does for sodium. Say these are the potassium channels, these are the sodium channels, okay? So more potassium can leave than sodium can enter. The interior becomes more and more negative, and then when we hit negative 70 millivolts, the rate at which potassium is leaving equals the rate at which sodium is coming in, and then we rest at negative 70. Now, I went over this with you in the past, but I think it's important to do this again. If you were to increase the permeability for potassium, meaning instead of having 100 leak channels for potassium versus 1 leak channel for sodium, and you were to do like 125 to 1, then you would be giving potassium more doors to travel through. You wouldn't be changing potassium's chemical driving force or changing its equilibrium potential, but you would be giving it more passageways for it to exit through. And thus the rate at which it could leave would increase, because there are actually then more channels, 125 to 1 versus 100 to 1. There's more channels for potassium to be able to leave through, so the rate at which it could leave would thus increase. Again, this hasn't changed the chemical driving force, it hasn't changed its equilibrium potential, but if you make the cell more permeable to potassium, then the rate at which it can leave is even greater. And you're going to end up with a more negative resting membrane potential. The interior is going to have to become more negative than negative 70 millivolts to reach a point where the rate at which potassium leaves equals the rate at which sodium comes in. You need a stronger negative electrical driving force to be able to sufficiently slow down the rate at which potassium leaves to equal the rate at which sodium comes in. And that's exactly what's going on here. At negative 70 millivolts, the voltage-gated potassium channels actually stay open. So for a transiently, for a short period of time, at negative 70 millivolts, the Hillock region, this is going to be true for every region of the axon too, as this happens in each region, transiently, you have an increased permeability for potassium here in this region, because not only are the leak channels all there for potassium, but now you have all of these voltage-gated potassium channels that are open too. So you've increased the number of doors for potassium to leave through. It can leave through both its leak channels, and now it can also leave through the voltage-gated potassium channels. So what's going to happen at negative 70 is, because the voltage-gated potassium channels stay open, potassium is going to continue to leak out at a greater rate than sodium can come in through its leak channels. So what's going to begin to happen to the neuron? The neuron is actually going to begin to what's called hyperpolarize. It's going to become more negative than negative 70. It's actually going to go down to about negative 75 millivolts. It's going to go below the resting membrane potential. And that is because extra voltage-gated potassium channels stay open. And you have a transient increase in permeability to potassium in this region, because again, not only are the leak channels for potassium there, but now these voltage-gated potassium channels are there. The number of leak channels for sodium is the same as always, so you've transiently increased the permeability for potassium above what it normally is because of these voltage-gated potassium channels, and thus potassium can continue to leak out at a greater rate than sodium can come in. And the Hillock region is actually going to hyperpolarize. And then finally, right around negative 75 millivolts, the voltage-gated sodium channels finally close. The voltage-gated potassium channels finally close around negative 75 millivolts. But now you're more negative than the resting membrane potential. And because the voltage-gated potassium channels have now closed and you've gone back to the standard permeability of approximately 100 to 1, you want to think about what's going to happen. All right, here's what's going to happen. Okay, at negative 75 millivolts, those extra voltage-gated potassium channels that were open, they all close. Okay, they shut. So now the extra doors that potassium had to go through are closed. Okay, and we're now below the resting membrane potential that was established at the standard permeability of 100 potassium channels for every 1 sodium leak channels. So if we're now at negative 75 millivolts, and we're back to the standard permeability of 100 potassium leak channels for every 1 sodium leak channel, you have to think about what is actually going to happen here. If we've hyperpolarized to negative 75 because of those voltage-gated potassium channels being opened and for longer, and the interior went down to negative 75, but the resting membrane potential with the standard permeability of 100 to 1, which is what we're back to now, generates a resting membrane potential of negative 70, then what's going to happen here when we're at negative 75? Well, let's think about this like, in a regular cell. Okay, if we get to negative 75 millivolts, and there are 100 potassium leak channels for every 1 sodium leak channel. Okay. At this permeability of 100 to 1, the resting membrane potential is established at negative 70 millivolts. That's the point at which potassium leaves at the same rate that sodium comes in. But now you make the interior negative 75 millivolts. That happened because for a very short transient amount of time, there were extra potassium channels that were open and more potassium was able to leave, and that drove the interior down to negative 75. But then those extra voltage-gated potassium channels closed, and now we're back to the standard permeability of 100 to 1. Okay, if that happens, if we're at negative 75 millivolts, we're hyperpolarized, and we're back to the standard permeability of 100 to 1. Here's what that means. There's a very strong negative electrical driving force, and with the standard permeability of 100 to 1, now the rate at which potassium can leave is actually less than the rate at which sodium can come in, because we made the interior negative 75. And what did that do? If we made the interior negative 75, that's going to slow down the rate that potassium can leave to an even greater degree. And it's going to increase the rate at which sodium can come in to an even greater degree. Okay? And now this is happening when those extra voltage-gated potassium channels closed. Okay? Those extra voltage-gated potassium channels are shut. We're back to the standard permeability of 100 to 1, and now we have a membrane potential of negative 75 millivolts. So that tells us something. At negative 75, in this circumstance of a standard permeability of 100 potassium channels to 1 sodium channel, the rate at which potassium is actually going to be able to leave in this circumstance compared to the rate at which sodium is going to be able to come in this circumstance, potassium is actually going to leave at a slower rate than sodium is going to enter. And what does that mean for the cell? The cell is now gaining more sodium ions than it's losing in positively charged potassium ions. It's losing more positively charged, it's gaining more positively charged ions. It's gaining more positively charged sodium ions than it's losing in positively charged potassium ions. So it's going to begin to become more positive. right? This is what's happening in the Hillock region, right? Actually, more sodium is coming in than potassium is going out through its leak channels at negative 75 millivolts. So if the cell is gaining more positively charged ions, sodium ions, then it's losing in positively charged ions, positively charged potassium ions, then it's going to begin to become more positive because it's gaining more positively charged ions, and it's going to begin to move back towards the resting membrane potential of negative 70. And then what's going to happen when we get back to negative 70 millivolts? When we get back to negative 70 millivolts, now we are truly back to the resting membrane potential. As the interior became more positive, the electrical driving force became more positive. Now there's less of a pull to pull the sodium ions in, and there's less of a pull to prevent the potassium ions from leaving. So once we get back to negative 70 millivolts from negative 75, we've made the membrane potential more positive. So you've reduced the negative electrical driving force to pull the sodium ions in by making the interior more positive. And you've also reduced the negative electrical driving force to pull the potassium ions backwards by making the interior more positive. So once you get back to negative 70 millivolts, you're going to be right back to the resting membrane potential. The rate at which potassium leaves is now going to equal the rate at which sodium comes in. And now you are truly back to the resting membrane potential. And once you understand all of this, you can finally, from my experience, maybe you were already good with this anyways, but I certainly wasn't. You can finally understand what those ridiculous diagrams showing action potentials actually are depicting. Let me show you. You've probably all seen this diagram at some point in your life. It depicts action potentials. I despise this diagram for a variety of reasons. I think to use something like this in an introductory means to teaching action potentials is cruel beyond belief. Because it can explain for a variety of reasons. An action potential in most people's mind is the actual wave electrical impulse that travels down the axon, non-decremental impulse that travels down the axon into the axon terminals and into the buttons. This really can't depict that. Okay, what this is, this can only really be, in my opinion, in one specific isolated region of a neuron, specifically anywhere, within the axon hillock or throughout the axon or axon terminal, but it has to be in a specific isolated region like the hillock. If this is just showing you what's happening inside of the hillock, it actually makes sense if all of the things that we discussed make sense. Let me explain. If this is just looking at the membrane potential inside of the hillock, great, right? We start off at negative 70 millivolts. And then what happens? The sodium ions from the dendrites move into the hillock region and make the hillock region more positive. It can actually make the hillock region hit threshold. If we hit threshold of negative 55 millivolts, what happens? Well, the activation gates on the voltage-gated sodium channels open. And you get a big influx of sodium ions into the hillock, which makes the interior of the hillock rise to positive 30 millivolts. And then what happens in the hillock? Well, at positive 30 millivolts, two things happen. The inactivation gates on the voltage-gated sodium channels close. So no more sodium can come in, which is why we get stuck at positive 30. Simultaneously, the voltage-gated potassium channels open and potassium shoots out, driving the interior back down towards negative 70 millivolts. We're not talking about refractory periods yet, but somewhere between negative 55 and probably like negative 65, the voltage-gated sodium channels reset. right? This isn't big to understand this diagram right now, but it will be in a second. So the inactivation gates open and the activation gates close. We're back to the original orientation. All right, but what do we see here? That's not really the big point of this. We actually see the hillock region hyperpolarize. It goes below -70. It goes down to like, -75 or so. You can see that right here. We actually hyperpolarize. See that listed here. Why do we hyperpolarize? Okay. The reason that the hillock region hyperpolarizes is because the voltage-gated potassium channels that were opened at +30, they stay open for an extended period of time. So when we're at -70, when we're back to -70, you don't just have the leak channels for potassium there, but you also have the voltage-gated potassium channels plus the leak channels open. So transiently, you have an increased permeability to potassium at -70 due to those voltage-gated potassium channels being open. So potassium continues to leak out at a greater rate than sodium comes in through the sodium leak channels, and thus we hyperpolarize. Okay, we become more negative. We go all the way down to, like, again, -75. Then finally, at -75, which is going to be, right about here, what happens is those voltage-gated potassium channels close. And now you're back to the standard permeability of potassium and sodium within the hillock, right? There's now 100 leak channels for potassium and for every 1 leak channel for sodium. But that standard permeability that's back is occurring while the membrane potential is now down to -75 millivolts. So with that standard permeability of 100 to 1, if the membrane potential is -75 millivolts, now actually the rate at which potassium can leave is less than the rate at which sodium can come in. So what you're going to begin to see is sodium come in at a greater rate than potassium leave because of the standard permeability of 100 to 1 is back and the membrane potential is hyperpolarized to -75. So as sodium comes in at a greater rate than potassium can leave, we begin to move back towards the resting membrane potential, which you can see depicted right here, right? We begin to actually become more positive. And then once we finally get back to -70 millivolts, right, we rest, right? We're back to the resting membrane potential because once we get back to -75 millivolts, we're back to the point at which potassium leaves at the same rate at which sodium comes in. All this diagram can be showing you, in my opinion, is what's happening in the hillock region. And this also is going to happen in each subsequent region of the axon and axon terminal as well. This does a nice job depicting the different events that are occurring in the different regions of the axon. But to look at an image like this and tell people this is the action potential, I don't even know what that's supposed to mean. Again, the action potential in most people's mind is a non-decremental wave of electricity that travels down the axon into the axon terminals and into the button. This diagram is the sequence of events that happens in the different regions of the axon. And you could say these are the sequence of events that happen in the different regions of the axon, during the action potential. But to say this is the action potential, I think does a huge disservice to actually understand what's happening during an action potential within a neuron. Or any cell for this matter. I mean, this same diagram, it's shaped a little differently, but is used for, cardiac muscle fibers, skeletal muscle fibers, smooth muscle fibers, neurons, sinylateral node fibers, which are a type of cardiac muscle fiber, but very unique. And I think it really complicates understanding in general how really any of those cells are truly functioning. So if you already understood this, great. If not, I hope I was able to give you some clarity as to what these diagrams actually depict if you ever see them again. And now we can talk about refractory periods. we can look at this image, and understanding refractory periods, if you understood all that other stuff, is really easy. So you have two different types of refractory periods. Highlighted kind of in this yellow color is what's called the absolute refractory period. The absolute refractory period, by definition, is the period of time when another action potential cannot happen. So the absolute refractory period happens from the time that the hillock hits threshold, negative 55 millivolts, until we repolarize back to somewhere between negative 55 and negative 65 millivolts or so. You can see that highlighted in yellow. Let's talk about that. So an absolute refractory period, the period of time when another action potential can't happen. Well, how is another action potential going to happen when we hit threshold and all the voltage-gated sodium channels activation gates are open and we're moving up towards positive 30 millivolts? I mean, it wouldn't make any sense. I mean, by definition, an action potential is occurring right now because all the voltage-gated sodium channels activation gates are open and sodium is rushing in. So you're not going to get another, let's do this like in red, you're not going to get another action potential while an action potential is happening. So this has to be part of the absolute refractory period. Again, we say the absolute refractory period is the period of time when another action potential can't happen. Another action potential can't happen also during repolarization back to about negative 55 to negative 65 millivolts. Why is that the case? Why can't another action potential happen during repolarization from positive 30 back towards negative 55 to negative 65? And the answer is it's all about the voltage-gated sodium channels. So as long as the inactivation gates are closed on the voltage-gated sodium channels, they can't open. It's completely impossible. As long as those inactivation gates are shut, nothing will open them. And thus there cannot be a large influx of sodium ions into the hillock during this period of time. So another action potential cannot happen. That's the second part of the absolute refractory period. During repolarization, let me say it one more time, during repolarization from positive 30 down to between negative 55 and negative 65, another action potential cannot happen because the inactivation gates on the voltage-gated sodium channels are shut and they can't open. They will not be opened by a voltage. Now, the end of the absolute refractory period occurs when the voltage-gated sodium channels reset. What does that mean exactly? It means that the inactivation gates pop open and the activation gates shut. The voltage-gated sodium channels reset between negative 55 and negative 65 millivolts. Right? And when these voltage-gated sodium channels have reset back to their original orientation, now they can open again. So if you can get the interior back to threshold of negative 55 millivolts, the voltage-gated sodium channels will be able to open again, and you will get another action potential. So the point is, as soon as the voltage-gated sodium channels reset so that they can be opened by a voltage again, that's the end of the absolute refractory period, as you can see highlighted in yellow. Okay. Now, what about the relative refractory period? The relative refractory period is highlighted in, I don't know what color that would be, like an orangish color. The relative refractory period is the period of time where another action potential can occur, but it's harder to get to that action potential than it normally is. So again, relative refractory period is the period of time where another action potential can happen, but it's quite difficult to get that action potential to actually happen. And there's two reasons. There's kind of two halves to the absolute refractory period. The first half to the absolute refractory period to the relative refractory period is this. Since I screwed that up, the relative refractory period, right, kind of has these two halves to it. It has a first half and it has a second half. In both halves, it's harder to generate another action potential than normal, but it can happen. So the first half of the relative refractory period is due to the fact that the voltage-gated potassium channels are actively open. So to actually get the interior of the hillock to rise to negative 55 millivolts, you have to get enough sodium into the hillock to overcome the fact that the hillock is transiently has an increased permeability to potassium, and lots of potassium is actually actively leaving the hillock region, making the interior even more negative. During the first half of the relative refractory period, again, just think about the fact that those voltage-gated potassium channels are open, and you have this transient increased permeability to potassium, which is making the interior of the hillock actively more negative. So you would have to get enough sodium into the hillock region to actually overcome the fact that the hillock is actively becoming more negative. You would need much more sodium coming into the hillock than normal in this circumstance to actually get the hillock region to threshold. Now, the second half of the relative refractory period, right, is here. Okay? The second half of the relative refractory period is the period of time when the voltage-gated potassium channels have actually closed up into the point until we're back to the resting membrane potential. So when the voltage-gated potassium channels actually shut, right, we're right around negative 75 millivolts. And I'm saying the second half of the relative refractory period lasts from the time that the voltage-gated potassium channels close at negative 75 until we're back to the regular resting membrane potential. And the reason why it's harder, for another action potential to occur is because, well, you need to get the interior of the hillock to rise by 20 millivolts to negative 55, rather than normally you have to get it to rise by 15. Right? Because we have to get the interior, let's erase some of this. You have to get the interior back to negative 55 millivolts in order for the voltage-gated sodium channels to open. And during the second half of the relative refractory period, yes, the voltage-gated potassium channels are closed now, but the hillock region is actually hyperpolarized, right? It's at negative 75 millivolts. So you don't have to get it from negative 70 to negative 55, 15 millivolt increase in positivity. You have to get it from like negative 75 all the way up to negative 55. So you need like a 20 millivolt increase in positivity. So again, during the second half of the relative refractory period, you can get an action potential to occur, but you're going to need more sodium ions to come into the hillock region than normal to get it to rise by 20 millivolts rather than 15. So that is the relative versus the absolute refractory period. The period of time, absolute refractory period, when another action potential cannot happen. And the relative refractory period, the period of time where another action potential can happen, but it's harder than normal for an action potential to occur. These are incredibly difficult concepts to comprehend, in my opinion, but they serve as the basis for understanding a huge variety of concepts throughout physiology and pharmacology, for that matter, and by extension, pathology. So before moving on, I hope you try to get a good grip as to what these different concepts mean. And if you need help, you know where I'm at. So, and I should probably say one last thing before I finish this. What's the point of an absolute and relative refractory period? Well, it's relatively simple, actually. The concepts themselves are, difficult, but why absolute and relative refractory periods exist is quite straightforward. It limits the number of action potentials that a given cell can generate in a given amount of time. The most important of those being the relative refractory period. If, for example, a neuron has voltage-gated sodium channels that all reset right at negative 55 millivolts, that neuron is going to be able to generate more action potentials in a given amount of time. If another neuron has voltage-gated sodium channels that don't reset until like negative 65 or negative 70, then that neuron is going to be able to generate less action potentials in a given amount of time. So the sooner that the relative refractory period begins, and thus the shorter the absolute refractory period is, the more frequently a neuron or any cell can generate action potentials. And this is really what makes the difference between, like, whether a neuron can generate 500 action potentials in a second or 1,000. It's going to be all related to really when that relative refractory period begins and the difficulty of getting the neuron or the cell back to threshold.